Okay. Now, was the derivative of cosine sine? Oh, it was negative sine, because if we go back through these and put in our critical points here, the tangent line has a slope of 0 at 0, pi, and 2 pi, right? You just have to determine in between them what's going on. Here it's decreasing. So the point of inflection, if it's decreasing on the derivative, would be a minimum. So -1. And then it starts increasing. So the point of inflection between concave up and concave down, if it's increasing, shows us the derivative would be a maximum. So if you graph that, -1, -1, make sure you label everything. We have 0, 0, by halves is -1. And it ends up being negative sine x. Okay. Now for new ones. It's not as easy to do the graphs for a tangent because you wouldn't recognize the graph when we get it. We could do it, but you'd be like, I don't know what function that is. So we're going to do it algebraically instead, using our trig identities. Okay? What's another way to write tangent? Sine over cosine. So f of x, which equals tangent x, and write small because this is a little long, is sine x over cosine x, right? So if we want the derivative, we're going to take the derivative of both sides. So, well, the derivative d dx represents derivative of sine x over cosine x. d dx is derivative of sine x over cosine x. This turns into what we did in 3.3, I believe, called the quotient rule. The quotient rule. We're going to be using that a lot today. How does the quotient rule work? What's it saying? Low D high minus high D low over low low. I like saying the ho ho because I feel like it means Snow White or something. High D ho minus low. Yeah, hold it. Oh man, I can't even do it now. Ho D high minus high D ho over ho ho. Okay, so we just plug in. Ho is the low. Cosine x times the derivative of the high. Sine is the high. What's the derivative of sine? I just did it. What's the derivative of sine? Cosine. So we put cosine x. Minus high is sine. High d ho. Derivative of cosine. Negative sine. All over ho-ho, or low-low, which would be cosine squared, right? And the 2 goes between the s and the x. Okay, so if we work this out, cosine x times cosine x is just cosine squared x. Negative sine x times negative sine x is negative sine x times negative sine x. Positive sine x squared plus sine squared x over cosine squared x. Okay? Well, the numerator should look familiar. Cosine squared x plus sine squared x. Do you know what that is? You have that yellow trig identity paper. This is a very common trig function. It's very useful. If I ever see a squared with cosines and sines, I instantly go to this. I think it's one of the Pythagorean identities on the left-hand side of your yellow paper. It's written in reverse order. Sine squared x plus cosine squared x. What does that equal? 1. It's so easy. It's so convenient. 1. over cosine squared x. And then, I believe that's a reciprocal function, isn't it? 1 over cosine squared x. 1 over cosine, we know. What's 1 over cosine? Secant. So 1 over cosine squared would be secant squared. So, the derivative of tangent x is secant squared x. Okay? Because the reciprocal function, this 1 over cosine is secant, so since it's 1 over cosine squared, it will be secant squared. Okay. Number 4, cotangents. Yeah, you won't recognize this graph either. So, what's another way to write cotangent? Cosine x over sine x. Because we know the derivatives of those individually, right? You can go with cosines and sines, we know the derivatives of those. So, we're going to take the derivative, ddx, of cosine x over sine x. The derivative with respect to x. Cosine x over sine x. Ho-de hi minus hi-de ho over ho-ho. What's the ho? Sine x times the derivative of the hi. Derivative of cosine. Negative sine x. Minus hi cosine x times the derivative of the low, cosine x, all over ho-ho, sine squared x. So, simplifying sine x times negative sine x. Negative sine squared x, or negative sine x squared. Negative cosine times cosine. Negative cosine squared x. All over sine squared x. Now again, I see the sine squared x and a cosine squared x, which makes me want to use the Pythagorean identity, but it's not quite the same. How can we make this positive sine squared x plus cosine squared x? So I could say that it was 1. Say what? Yeah, we could. What's another way? That would totally work. I didn't think about that before. Factor out negative. Either way, eventually a negative is popping out, right? So, negative would be sine squared x plus cosine squared x over sine squared x. So the numerator, using that Pythagorean identity, sine squared x plus cosine squared x equals what number? 1, so we'll have negative 1 over sine squared x. Well, if you see 1 over sine, that should be an idea to look at your reciprocal identities. What's 1 over sine? Cosecant. So 1 over sine squared, or negative 1 over sine squared would be negative cosecant squared x. So the derivative of cotangent is negative cosecant squared x. Is this making sense? Okay, cosecant. What's the derivative of cosecant? Well, is there another way to write cosecant? Oh, we can use reciprocal, 1 over sine. Is that still using our quotient rule? I think so, isn't it? Just the fraction. 1 over sine x. Okay, so I'm going to do the derivative with respect to x of 1 over sine x. Okay, ho-de hi minus hi-de ho over ho-ho. Ho is sine times the derivative of the hi. What's the derivative of 1? 0. That's so nice because that's going to cancel out. Ho-de hi minus High is 1. Below, what's the derivative of below? Cosine x over ho-ho. Sine squared. So because of that 0, that first set cancels out, and we're left with negative cosine x over sine squared x. Ooh, that looks really familiar too. What happens when we have cosine over sine? Tangent. Now, but there's 2 sines, so I'm going to break this up. I have 2 sines times, but we only have 1 cosine. So the cosine can only go with one of them, correct? We have negative 1 times cosine. Oops, oops, oops. So that should be to the first power. Better. So our reciprocal function, negative 1 over sine, would be what function? Negative cosecant. So negative CX, and then cosine over sine is I feel like I'm hearing both, but it's cotangent. And this is the derivative of cosecant. So it's interesting, the derivative of cosecant actually has cosecant in it. Okay, so the derivative of cosecant is negative cosecant x times cotangent x. Okay, we're going to do one more that didn't get put on these notes. Underneath this box, we haven't done secant. F of x equals secant x. What's another way to write secant? 1 over cosine x. So I'll let you do this one by yourself. d dx of 1 over cosine, find the derivative with respect to x of 1 over cosine x. Okay, work that out all the way to the end by yourself. Stand up when you think you have it. Yep, and make sure you put d dx of secant equals that. Good. We have a sign issue here. This is all right, except for it should be positive. So, and a minus sign right there. And then a minus times a minus would make it a positive. Good. Great, I think we're getting it. Everyone's getting secant x times tangent x, which is the same as saying tangent x times secant x, right? Okay, awesome. Okay, quick review. Claudia, what's the derivative y prime of x to the 5th? Claudia, what's the derivative of x to the 5th? Good. Okay, and this one. Ethan, what's the derivative of 3x to the 4th? 12x to the what? Great. Okay, in this box we're going to list all of the trig functions that we just got. There are 6 of them, so make sure you are writing using your space so you can fit 6. The derivative of sine equals, what's the derivative of sine? Cosine x. P dx of cosine is not sine. Those don't just go back and forth. It is negative sine x. Those are the two you use most often, but you need to have these ones memorized as well. The derivative of tangent. Yep, secant squared. Now these next two get kind of long. The derivative of cosecant. Has a cosecant in it, right? Negative cosecant x cotangent x. Okay, then secant. What's the derivative of secant? So that also has part of itself in it. And the last one, cotangent. Cotangent is negative cosecant squared x. Okay, make yourself flashcards if you have to. Start memorizing those. Any questions on them? Hey, flip it over. You can always, if you get stuck and you're like, oh shoot, I'm on the test and I need to remember what the derivative of tangent is, you can work it out really quick. You've seen how. It just takes time. Time is very valuable on the test. Okay, we are going to go through and find the derivatives of all of these. Now, what rule would we use on number 6 to find the derivative of 3 sine x? It's the product rule. Now I want you to notice what happens when we do number 6 and number 7. Okay, so we're going to take the derivative of y with respect to x and the derivative of 3 times sine x. Okay, so what is the product rule? First d last, not times, no, plus last d first. Okay, so think of this as quotient rule is the minus. Ho d high minus high d ho over ho ho. What does a fraction bar look like for division? Does it look like a minus sign? Yeah. So minus fraction bar. Yeah, and when we're timesing, we have first d last plus last d first. This is the product rule, isn't it? Isn't a product rule like a sideways time symbol? Addition, product. I don't know, I'm just trying to give you a way to remember the minus and the plus. Product is just rotating your plus and minus signs. Fraction bar looks like subtraction sign. I better not touch my white shirt since I got black all over me now. Okay, you got to keep those straight. So, dy dx. I would probably start writing further to the left so we have room for number 7. First is what? 3. First d last. Derivative of the last. Derivative of sine. Cosine. First d last. Plus last is sine. D first, what's the derivative of 3? 0. Oh, interesting. So that cancels out, and dy dx is just 3 cosine x. Okay. Number 7. And do the derivative with respect to of y with respect to x. And take the derivative with respect to x of 3 cosecant x. Because if we use the product rule, if we're taking the derivative of the 3, what will happen every time? It will cancel out. So we can use this as the constant rule. That constant is going to make the other guy cancel out. This term will always cancel out because of the constant. So we can pull the 3 in front and just do the derivative of cosecant. The derivative of cosecant is, so we get negative 3 cosecant x cotangent x. dy dx equals negative 3 cosecant x cotangent x. You can't use the product rule too, you'll just notice that that term cancels out to 0. Okay, number 8 is definitely a product rule. Can I just pull out something in front like the 2? Can I just pull that in front like I did on number 7? No. So you definitely have to do product rule on this one. dy dx equals, okay, first d last. What's the first? X squared. D last. What's the... Can you guys see the 2 terms? Make sure, because once we get to our next lesson called chain rule, you have to be able to identify the 2 rules, the 2 pieces. Make sure you're... If you can't identify them, please let me know. First and last, derivative of the sign is cosine. Plus or minus, guys? Which one is it? Plus. Last. D first, derivative of the first. 2x. Now we don't usually put a 2x after sign. Those things generally go in front of sign. So I would say x squared cosine x plus 2x sine x. Would this be the same thing as factoring out an x? You're writing x cosine x plus 2 sine x. Is that the same? Do they both have x's? So I pulled one out, which cosine still has an extra 1. I just want you to get familiar seeing the same answer in different forms. Number 9. How many product rules are there in number 9? Depends how you look at it, right? Is there a product rule right here? You could do a product rule, but you would notice one will have a 0 and cancel out once you take the derivative of the 3. So that would just be like the coefficient dy dx. I'm going to pull out the 3, and then I'm going to take the derivative of cosine x plus, does this guy have a constant? Can I pull out pi? Because the derivative of pi ends up being 0. So if that has a constant, you can pull it out and avoid the product rule. So 3 times the derivative of cosine. How about what's the derivative of cosine? Good, negative sine x. Plus pi times the derivative of x. Jonathan, what's the derivative of x? 1. Great. So the derivative here would be negative 3 sine x plus pi. Okay, number 10 is a little different. Given f of x equals x cosecant x, and the tangent line x equals pi halves. I'm going to give you this blue packet here, and it has the stuff for all year long. It says, when you see these words, this is what you should be doing. Okay, so you get If you don't know what to do, maybe refer to this. And, oops, it goes this way. Oh, so you see tangent line, you should be taking the derivative. And when it says at a particular moment, what should you be doing? Yep, plug it in. So, let me give you this, though. I would say the first page front and back is stuff we already know. So the first page front and back is useful right now. And then we'll get more as the year goes on. Okay, slow this down. Okay, so if you look, the front has all these things about limits. Flip it over. Number 13. What does number 13 say? Okay, find the slope of the tangent line. So if you're looking at tangent line, what does it tell you to do? Find the derivative. Okay? Which is exactly what we said. And then, when we have, at a certain point, we have to plug in. So, the derivative. Well, I have two pieces. Part 1, part 2. Being multiplied, so I have to apply the product rule. F prime of x equals firsty last plus lasty first. Read, what's firsty last going to look like? Good. Plus lasty first. Gisu, what's lasty first? Good. Okay, so we get negative x cosecant x cotangent x plus cosecant x. Do they have anything in common? You could factor out if it was handy at some point. Do these terms have anything in common? We both have a cosecant, so I can, if I wanted, sometimes it's useful to factor out what they have in common, cosecant, which leaves me with negative x cotangent x plus, ooh, if I factor out, it means I'm dividing. What's a cosecant divided by a cosecant? 1. So, or that. Okay, but that's not our answer. This is f prime. What do we do now? Plug in pi halves. Okay, you still have those yellow reference sheets? We need to know a few of these things. Oops, I need to plug in pi halves. Cosecant of pi halves. Now, if you don't know that, you could use your reciprocal functions. What's the reciprocal of cosecant? 1 over sine. Do you know sine at pi halves? Sine at pi halves, I just draw my little... There's pi. What's sine of pi halves? Okay. So what's cosecant at pi halves? You have your yellow reference sheet? Oh, she has it right there. Those are things you need to start memorizing. You need to know their values. Cosecant at pi halves. So you just go down here to get pi halves is 1, because if sine is 1, what's the reciprocal of 1? 1 over 1, it's still 1. Minus pi halves times cotangent pi halves. Well, if you don't know cotangent pi halves, ooh, anything really with I was thinking pi fourths. Cotangent pi halves, that's something, that's the easier one to, Well, tangent's easier, isn't it? Tangent's easier to memorize. You know tangent and pi halves? What happens here? Tangent looks like this. This is pi halves. Which means tangent and pi halves is undefined because it has a division by 0. It has some number divided by 0. If you flip that, 0 is on top over some number. So cotangent would be 0. Okay, and timesing by 0 is nice, gone, and we get 1 times 1. Huh, all that work. But we're not done. What does this 1 mean? Where? The slope of the tangent line at pi halves. Is that all it asked us? It wants the line, the equation. So this is the slope of the tangent line at pi halves. Okay, we're not done. We want a line, meaning we want an equation. What's our friend that gives us equations? We need a point slope form. But this is only like our x value, right? Or, excuse me, our y value. So, what? That's m. Yeah, that's m. This is our x value. This is m. That's our x value. So, we need to find the y value is. So, we plug in pi halves into the original. The original is x cosecant x. I can put it over here. It's pi halves times cosecant pi halves. That is cosine, not cosecant. Okay, cosecant's reciprocal. But what's cosecant's reciprocal? 1 over sine. Sine at pi halves is 1, and the reciprocal of 1 is just 1. So we have pi halves times 1, which is just pi halves. So our point is pi halves by halves. Okay? So I'm going to let you find the equation now. Here's our point. Here is our slope. Remember the y minus y1 equals m times x minus x1. That's why we touched that at the beginning of the year, because we use this all the time. Got it? Now, if it doesn't say which form to put it in, can you technically stop here? Okay, fine. Now, interestingly, if you continue on, we get x minus pi halves. Scoot this over by adding it, and we actually get, so this is it too. That's an interesting thing to think about, because it's just that diagonal line through the first quadrant at a 45-degree angle. Cool. Okay, flip it over to the back if you would, where it's blank. Oh, you don't have a blank side. Oh, mine has a blank side. That doesn't work. Okay, get a piece of paper out, I guess. Yeah, it's going to be a lot. You need a lot. Story problem. It's not on your notes, but it's very important, so I thought I'd cover it. This is cool. We've done physics. Maybe you've already been introduced to this, and it'll be easy for you, but if you haven't done physics, it might be kind of new. Okay, so I think that last one is example 11, or 10, so this is example 11. Oops. Today is the 21st. Okay, a weight hanging from a spring is stretched 5 units before its rest position. A weight hanging from a string is stretched 5 units beyond its rest position. The rest position would be when the S equals 0. It would be resting. And it's released at time t equals 0 to bob up and down. Its position at any later time t is position at any later time t is S equals 5 cosine t. Four questions. What is its velocity, speed, and acceleration? At time t. Also, describe its motion. Who's done something like this in a physics class? No? Oh, that's really writing uphill. Okay, so let's. Are you still writing or are you done? So we have. This is my axis. Here's resting position, S equals 0. My spring has a weight. At rest would be hanging at S equals 0. Okay? It is stretched 5 units beyond its rest position. So that'd be S equals 5. And it's released at time t equals 0 to bob up and down. Okay, so what is the velocity? What? Yeah, here's our position function. Velocity is the derivative of the position function equals the velocity function. So we have 5 cosine t. Take the derivative of that, Joanna. What would the derivative of 5 cosine t be? Because it was pulled 5 beyond its rest position. What's the derivative of cosine? On your notes, derivative of cosine. Okay, so if we have 5 cosine, we get negative 5 cosine. Okay. So there's the velocity. Do you remember what speed's relationship is to velocity? The absolute value. Speed equals the absolute value of velocity. So it would be the absolute value of negative 5 sine t, which is just 5 sine t. Acceleration. Read, how do we get acceleration? Rate. S double prime, and which is the derivative of the velocity, which is acceleration. So if the velocity is negative 5 sine t, Rebecca, what would the derivative for their acceleration be? The derivative velocity of negative 5 sine t. Yep. Great. Any questions there? Okay. Let's describe its motion. What happens to the spring as time passes? Okay. Now, notice this. You remember AH and K? S equals A times cosine of T minus H plus K. What does that multiplier mean? 5. Ooh, because why is it a constant up, down 5? Why is it going to go up to negative 5? There's a word. Amplitude. Thank you. We graphed that. Oops. We graph that. Cosine, but it starts, our amplitude is 5. So it's going to start at 5, and then it's going to go down to negative 5, and then go up, and just be oscillating over and over. Right? This is our S function, and here is 0 of the spring. Okay, so as time passes, the rate moves up and down between negative 5 and positive 5. S equals negative 5 and positive 5 on the S-axis. Do you know why we're calling it the S-axis? What? I can't hear you. Position. And we're also dealing with a spring, which is convenient. Okay, so as time passes, the weight moves up and down between, you're going to have to do some of these on your homework, which is why we're going over it. So between S equals negative 5 and S equals positive 5. Remember, that's the position on the S-axis. The amplitude of the motion is 5, and what's the period? Period is when it completes one cycle. Pi. Well, not pi, actually. 2 pi. The amplitude of the motion is 5, and the period is 2 pi. Cool. B, if there's a multiplier in front of this t, there's a multiplier in front of that t. Okay, so homework you have on your blue slip. Also, I said I would give you this. Oh, maybe I didn't. Oh, I thought I copied it. Maybe I did not copy it. Okay, well, we still have 3 classes. But I did want to give you this aquarium problem. It has more velocity and acceleration problems on it. And understanding a graph. Well, you also have a section 3.5. But 3.4 is due next time. 3, 4, 5. Yep, this will be due next week. So bring 3, 4 completely done next time. See you later.